Yeah, good morning, everyone. So it's my great honor and pleasure to have Professor Jianpei here to give us a talk on very interesting topics related with data science and analytics. The topic is about, practicing the art of data science. And before Professor Jianpei to give his interesting talk, and it's a very innovative talk, let me give a very brief introduction, Professor Jianpei. I know a lot of people already know him very well from his book, from his papers, but still, I have to introduce him here. And Professor Jianpei is working very hard to facilitate efficient, fair, and sustainable usage of data and data analytics for social, economic, and ecological good. Through inventing, implementing, and deploying a series of data mining principles and methods, he produced remarkable values to academia and industry. His algorithm has been adopted um, by industry, open source toolkits, and textbook. His publication has been cited intensively. He is also he's also very active and productive volunteer for professional community service, such as chair ACM-CKDD, running many preliminary academic conferences in his area, and being the editor-in-chief or associate editors for the flagship journals in his field. He is recognized as a fellow of the Royal Society of Canada and the Canadian Academy of Engineers, ACM Fellows, HBE Fellows. He received a series of prestigious awards such as KDD Innovation Award, ACM KDD Service Award, and HBE SEDM Research Award. Currently, Jianpei is a full professor in Simon Fraser University, Canada. So without further ado, please join me to welcome Professor Jianpei's excellent talk.
Thank you very much. Thank you, Lei, for having me here. 祝大家新年快乐，祝大家新年快乐。Yeah, so Lei, I should talk about 45 minutes and then leave time for question answer. Okay, so today I'll share with you my experience in practicing the art of data science. So we all know when we have to call a subject an art, a science, like a data science, like a computer science. Essentially, it is not a science yet. Indeed, for data science, it is really a mix or a combination of some scientific principles, for example, like statistics, like mathematical principles, and also with a lot of engineering efforts. For example, in machine learning, in computer science applications. And one important component is the art, is the creative ways to combine these several things together. So that is the reason why I said that the important thing for data science is the art. Indeed, if we look at the whole data science, essentially, the data science provides domain-oriented end-to-end solutions to interpret data to knowledge workers. So it connects the applications with some general scientific principles and tools. We go through the data collection and pattern mining, and also the exploring the patterns using statistical methods, and then we construct models to predict our forecast, and then we deliver the findings to applications, put the results into good use. And this would not be a one-shot effort. Indeed, we have to do it again and again in an iterative way. So to that extent, data science practice is really an end-to-end solution. And hopefully we can deliver interpretable knowledge. So I'm not the only one saying data science is a combination of science, engineering, and art. Indeed, there was a very well-known article in the Harvard Business Review says the key skills for data scientists are not the abilities to build and use deep learning infrastructures. And definitely this is one of the hot topics nowadays, but data science is much more than that. It says instead, the data scientists should have the abilities to learn on the fly and to communicate well in order to answer business questions, explaining complex results to non-technical stakeholders. Let me give you one example to show what I mean by the act and what I mean by combining applications. More than 10 years ago, indeed it's 16 years ago, we look at the problem of mining frequent closed partial orders. The general idea is the following. Okay, just suppose you are in a bank and you observe the order of those bank users open different kinds of accounts. Then you record what kind of accounts they open. For example, here you can see, let me use the pointer. Okay, laser pointer. For example, you can see they first open the checking account and then to the money market account and the mortgage account and so on. And then you may find some sequential patterns. But because the accounts may not have the directly order, so some accounts may open in different orders, but that's fine. We can form a partial order to summarize such activities. Well, we published a paper in a quite good data mining conference, ICDM, and then later on, indeed, we published the results in the IGP transactions of data engineering, where Professor Lei Chen is currently the associate editor-in-chief. And our paper was read by a few people, and then we still got 100 something citations. However, in our paper, we just use some bioinformatics applications as examples. Then this is a typical way of writing a data mining algorithm paper. But can we make these algorithms more useful, more approachable, more beneficial to real users? Later on, we work with researchers in software engineering, and they apply our approach in solving the problems of API usage mining and use the API usage patterns to recommend APIs. You can see that the citation is dramatically higher than our original paper. And indeed, we make up the first API pattern-based recommendation package for software engineering. So this is a very quick example to illustrate my idea of data science. The lessons we learn here are threefold. First, data science should provide domain-oriented end-to-end solutions. Second, machine learning produces good models. Data science should help people obtain domain knowledge. Last, we need interpretability. We need understandability. This is the key for the end users to use our machine learning tools. Because we talk about the interpretability, explainability, which is a very hot topic nowadays, let me go one more step to give you some deeper discussion on that. The state of the art of deep model interpretability can be divided roughly into three categories. The first approach uses this hidden neuron analysis. The general idea is that we can visualize or revert, map, or label features that are learned by hidden neurons. The major drawback of this approach is that, well, even you can quantitatively analyze every neuron, but it does not provide much actionable and quantitative interpretation about the overall mechanism of the whole model, because the whole model is not a simple summation of all the individual neurons together. The second approach is the model mimicking methods. The idea is that, well, we can mimic the classification function of a target model, and then we build a transparent model that is easy to interpret and has a high accuracy. However, in this case, you have two models. One is the original model, one is the model mimicking the original model. And then, because you try to reduce the model complexity of the mimicking model, there is no guarantee that a deep model with a large VC dimension may still successfully be imitated by a simpler shallow model. And the third approach is the local interpretation methods. The idea is that we can compute and visualize the important features for an input instance by analyzing the predictions of its local perturbations. But the drawback is that positively, their indistinguishable instances may not be explained consistently. Meaning, maybe we have two samples which are very similar to each other, but they may have very different interpretation. So there is a series of challenges in deep model interpretation or explanation. And Professor Cynthia Rudin in Natural Machine Intelligence has a paper in 2019. She said, there are several challenges. First, explanation may not be faithful to the original deep model. Second, explanation often do not make sense because they may not be faithful. And also it may be on a different model. Or explanation may not provide enough details to understand what a black box model is doing. And black box models are often not compatible with the situations where information outside the database needs to be combined with a risk assessment. And the black box models with explanation can lead to an overly complicated decision pathway ripe for human error. So in conclusion, she says, we should stop explaining black box machine learning models for high-stake decisions and use interpretable models instead. So that's a very strong argument for deep model interpretation and explanation. Now, based on our research, we propose a requirement for deep model interpretation. We want the interpretation to be exact and consistent. What do they mean? We say a model M is an exact interpretation of another model N if this M is mathematically equivalent to N. Meaning we want to have two models. If one interprets the other, these two models have to be mathematically equivalent to each other. Also, we want the interpretation to be consistent. This means if we have a model M, it is a consistent interpretation of another model N if this M provides similar interpretations for classification on similar instances. In other words, if we have two instances, they are very similar to each other, their explanations or their interpretations should also be similar to each other. The key is now how we can transform a black box model into a white box to provide exact and consistent interpretation. So in KDD 2018, our group developed the first exact and consistent interpretation of PLNNs. We start with the piecewise linear neural networks because those networks are popularly used in deep learning. For example, when you use ReLU, you use MaxR, you essentially use PLNN. The key idea here is that a PLNN is mathematically equivalent to a set of local linear classifiers. Then we have a local linear classifier that can cover the instances within a convex polytope in the input space. So using these ideas, we can construct mathematically equivalent models and then provide interpretation. We even developed an open box, which is a software suite that provides exact interpretation for PLNN by an equivalent set of local linear classifiers in closed form. Now, each instance can be interpreted using the corresponding decision features. Let me quickly tell you some intuition behind our method. Well, let's say how we can get the exact interpretation of a single instance. Because each neuron indeed takes the input and takes a piecewise linear activation function to produce the output. So the activation status of a hidden neuron can be regarded as a k-array code. Essentially is that you have this k and then you know the corresponding output. Okay. Then you have a neural network, you have deep network. If we aligned all those neurons into a string, then we can look at what's the status of each bit, right? And using the status of each bit, we can construct a new training example. And then using this training example, we can construct a classification function on those states. And this classification function on those states mathematically is equivalent to this deep neural network. So that's a very simple and intuitive idea behind how to construct the exact interpretation. Now, in order to find consistent interpretation, what we can do is that we can try to find the polytopes where for any x and x prime, which are close to each other, their configurations are the same. Okay, and then that can be do is that we can use these as observations to construct the to compute the polytope and construct the interpretation. So in practice, how does it work? We construct a training data set like this, and then we build a deep model, which is the prediction result. And then our interpretation construct these convex polytopes like this. And we extract the decision functions, decision boundary, and we construct the corresponding linear classifiers. You can see those linear classifiers indeed interpret these deep neural network. Let me show you a little bit about the experimental results here. And we can compare our approach with the state-of-the-art, the Lime approach. And you can see our approach just have a very nice fitting of the result, while the Lime indeed has a lot of such up and down on each point. So it is not very as smooth as our approach. And also in terms of the consistency, our approach is clearly outperforms the Lime method. One challenge to put the interpretation into real application is that many models are indeed built in cloud services. In other words, users do not have access to model parameters or training data. Can we provide in exact and consistent interpretation for those deep models hidden behind the APIs? We have a few key ideas to do this. First, we can try to find the decision features for an instance to be interpreted by computing the closed form solutions to a set of determined linear equation system. Then we use a small set of sample instances to construct the equation system. And our approach indeed comes with a theoretical guarantee. The exact decision features are identified with probability 1. We prove in our paper the probability is 1. But probability 1 means that we may still make mistake, but the chance we will make mistake is very little. Let me skip the details here for the interest of time. So very recently, we all move forward to try to understand deep model complexity. The idea here is how we can measure the complexity of deep neural networks with arbitrary activation functions. The major idea we use here is that we can use a piecewise linear framework to approximate a given deep model with any curve activation function and guarantee the approximation quality. And then we can compute an upper bound of the number of linear regions as the complexity measure. And we show in our paper that using these complexity measure, we can understand and control overfitting. And this is very important because it can help us to understand when overfitting happens and when we can stop the learning process. And indeed, if you are interested, later in next month, in April, in the SIAM Data Mining Conference, we will have a half-day tutorial on deep model complexity. So in the first half of my talk here, I try to deliver the following message. First, data science is much more than just developing new algorithms or new models. It is much more than just tuning models. And indeed, domain-oriented end-to-end solutions are highly valuable. In order to deliver end-to-end solutions to users, we need to provide interpretability. We need to provide the ways so that the users can understand the model, can understand the results. And the key here is that knowledge learning with data science is to turn black box models into white box models. We see many data science research nowadays try to develop many different models. Therefore, a very natural question is whether data science is trying to reinvent or invent more views, or instead, we may be able to assemble views to build more powerful vehicles. Let me use another example to illustrate. Graph is a very important data model because arguably, graph is the last resort for the curse of complexity in real applications. We may have so many applications like geographical networks, relations, and social networks, where you have so sophisticated relations and structures that you cannot use one data structure to describe all of them. Although locally, you may have some well-structured information. Then graph can give you the last resort. To that extent, graph indeed is a divide and conquer in modeling. Why? Because individual nodes and edges are well structured. So this is the part you can conquer. You can divide your whole information into individual nodes and edges and conquer them. But overall, you still reserve the flexibility and the sophisticated nature of the information. So it is a graph. Mining graphs and networks is highly interesting and attracts a lot of attention because it provides us the whole freedom to tackle the problem from many different possible views and many important tasks. For example, you can do that at the micro level. You look at the nodes and edges. You can do that at the macro level, look at the global structures and properties. And of course, you can stay in the middle. You do the intermediate view. You look at the local structures and behaviors. Don't forget, you have a very important factor called time. You can look at the change. So you have a temporal view. There are many tasks you can do, like a pattern mining, like a classification, prediction, clustering, outlier detection. But graph computing is very, very challenging. Why? If you think about it, for efficient data processing, we always explicitly or implicitly hold two assumptions. The first assumption is that, well, the data should be well structured. The second assumption is that ideally, the data should be synchronized. But all those two assumptions are not holding anymore in graph and network data. Yes, we have some basic structures, but many unstructured elements. And because the graph can be updated in a highly synchronized way, so we don't have the synchronization in graph data. My group has been working on graph computing since 2004. And indeed, we cover the very large portion of graph computing from data to intelligence. At the lowest level, we work on graph construction, entity and relationship identification, and construct graph databases to store and index graph data. And then for specific graph data, for example, geographical networks, social networks, we have specialized graph databases. And then on top of those graph databases, we have different kinds of tasks like query answering, pattern mining, information flow, propagation and inference analysis, privacy preservation, machine learning. Nowadays, if I give a talk and I don't talk about machine learning, people will think, oh, this guy is not serious about it. Okay. So let me use machine learning as an example to explain. Well, we do classification in graphs. Indeed, there are a lot of things we can do. We can do, what to classify, nodes or edge. You even do the future work for subgraph classification. And what kind of information you want to use to do the classification? You can use attributes, views, neighborhood patterns, and many other pieces. And you can also consider time, change, time. Those are important friends and also important challenges for classification. We did a series of studies on graph classification, and the papers were published in not bad places, but they were not very well cited. People didn't like them. Let me put it that way. Or people did not find them very useful. Clustering is another important graph mining problem. And there are many different ways in graph to define clusters. You have the whole freedom to do that. There are more information may be used, such as rich information in nodes. You may work on the dynamic clusters, dynamic communities. So, for example, one interesting clustering problem we work on was the gangs in war. The idea is that we try to find the clusters of, for example, the voters. so that the voters, they like each other very much. And the voters in different clusters, they fight against each other a lot. And we can also do the dynamic thing, look at the density bursting subgraphs. For example, this is the traffic in Chicago downtown. We can find the clusters at different times. Again, we published a series of such graph clustering papers in top conferences like VLDB, KDD, and so on. And people could not find them directly useful in their follow-up studies. Why? We learned a lesson here. That is, the way of one specialized solution for one specific problem is not scalable. From the academic wise, people cannot see the general principles and the methodology if we solve one specific problem at a time, and different problems do not really connect each other well. From the industrial point of view, people will think, well, they really want the general and adaptive solutions for many problems of the same or similar kind instead of one problem at a time. So to that extent, data science should be really connecting the problems in vertical applications and general solutions. What people really want is the off-the-shelf solutions, scalable in deployment, so that they can try to encapsulate the problem's transformation into those customizable units. What does that mean? Let me give you one concrete example to understand this. For example, we work on network embedding. Network embedding, indeed, in general, the idea is that we try to transform networks into vector data so that we can use general machine learning methods on graphs. In other words, we do not invent another machine learning approach. Instead, we try to turn graph data into vector data. And of course, sorry, when you do the transformation, when you do the embedding, you have to lose some information. You have to make the trade-off. Then the key is how to preserve the information in network embedding. So that's what I mean. You have a graph. Ideally, if we can transform the graph, we call embedding, into a vector space, then we can use the existing machine learning approach. So we have a series approach on these graph transformation, graph embedding. For example, we can do the asymmetric transitivity preserving embedding. The idea is that, well, in a directed graph, a node may serve two different roles. One is the source, one is the target. Because it serves as a different roles, indeed, instead of mapping one node into one vector, we try to map one node into two different vectors, one representing the source, one representing the targets. So that is our KDD 16 paper on this topic. And also in network, there are different types of structures. For example, we have microscopic structures, which focuses on the pairwise relationship or similarity between nodes. We also have the mesoscopic structure, which constrains in a higher structural level. That is, for example, a community. Then, can we do the network embedding preserve both structures? The idea here is that we can do the modularized non-negative matrix factorization. Now, network embedding becomes a very hot direction because it really helps the users to transform their graph mining problem into standard network machine learning problem and use the well-established machine learning methods to solve their problems. And we also have a survey on network embedding. If you are interested, I suggest you to take a look at it. We have a whole series of ongoing work on network embedding. Indeed, we also very recently, we extend the graph mining approach to natural language processing. We try to use the graph representation for semi-structured data and use that for question answering. So you can see data science, in my opinion, should be connectors. They should connect the vertical application problems with general solutions. The power of data science is on the frameworks, on the methodologies, and on the platforms. Another interesting project I would like to talk about the data science, indeed, following this connector way, is our recent project working with the Microsoft team on scaling out NLP applications to over 100 languages. This is really data science in action. And the idea here is that, well, building NLP models typically needs a lot of data. But most of the language in the world, it is very hard, if possible at all, to obtain such training data. So the idea is that we really need to use different kinds of data science approach to do data augmentation, to do cross-lingual machine learning, to try to include users in the loop to let the users to help us. Particularly for data augmentation, we can do the translation data, we can do the synthesized data, we can build the linkage among different data sources. And for cross-lingual machine learning models, we try to do the effective knowledge distillation. We try to use reinforcement learning to help to build the models, and we use the graph representation. And it is very important to have users in the loop, have users at the center of the loop. We develop the effective understanding of those implicit feedbacks from user behavior. Our recent progress include several papers. I really want to highlight is that in the World Web Conference this year, we will have a one-day tutorial on with an exact topic is called Scaling Out NLP Applications to 100 Languages. This would be, I promise you, this would be a very interesting and inspiring tutorial there. And indeed, many of those applications already go online into production last year. So in summary, as I said, data science is a connector. It connects general specific principles and tools with application domains. Data science should provide domain-oriented end-to-end solutions and should produce interpretable knowledge. It goes through several important steps from data collection, data cleaning, pattern mining, model building, and also the model applications. There are a lot of things we can do with data science. For example, one important future work is data strategies for enterprises and organizations. In an organization, there are several important strategies. For example, data should be used as assets and resources. Then we need to have the techniques to price data. Privacy is very important, so we need to have a privacy assessment and GDPR enforcement. And we also should have data as the media to build collaboration within the organization and between different organizations. In such sense, business products driven by data collaboration are very, very important. And also, we need to do the organization optimization. And then we need to have the corresponding techniques to strengthen the communication, data integration, and sharing. Indeed, just last week, I was in a podcast process. The podcast will be announced pretty soon. And the host asked me one question. Oh, if you were given a chance to give 3 advices for the 6 O's, like a chief CEO, CIO, what would you say? I thought about that. I would give 3 things. First, data is a crucial resource, as important as finance. If you have a CFO in your company, you should have a CDO, Chief Data Officer, in your company too, to manage the critical resource. And don't just look at your physical products. Look at your process. Try to datafy your business. You are much richer than you think. Data is a double-brain sword. Please take privacy and security seriously, because privacy and security can help you. They may also hurt you. You need to be careful about that. And as an initial process, we have I wrote one survey paper on data pricing, and which is a combination of economics and data science. And also on privacy, we have some existing work, particularly, for example, the privacy preservation in social network. And for the interest of time, let me skip this part. Okay. But one thing I want to emphasize is that data science is still an art, like privacy as an example. Although there are many studies on privacy, but privacy problems are still not solved, because we still see, well, many privacy models one after another, but still privacy leaking, abusing instance again and again. There are very few models have been put into practical use. The major obstacle here is the strict assumptions about the attacker's background knowledge and data utility. And similarly for data science, many models have very strong assumptions far away from the practice, which prevent them from being implemented, deployed successfully. And if I'm allowed to say one more thing about privacy, is that privacy in many cases is different from what academia looks at it. Privacy, after all, is about the right to be forgotten. It's about being free from being observed or disturbed by other people. So we need to understand the nature of privacy intrusion. Essentially, it is the unauthorized post-transaction data retention or the inappropriate second use of data. So to solve the privacy problem, of course, we have different kinds of models, but very important, one thing we need to explore is the persistent big data applications can naturally lead to privacy challenges. We need to think about how to stop the offline and continuous AI model training using the data that should be forgotten. There's still a long way to go. So that's all for my talk. Thank you again for having me here. I'm happy to answer any questions.
Thank you again, Professor Jianpei's excellent talk. Actually, it's very interesting. So any question from audience, and then you can unmute yourself and then ask. If you want to type your question in the chat box, I will read it out for you. Please go ahead.
Okay, Jen, thanks. I started to ask a question when other people are thinking. The talk is really good. I really enjoyed it. A lot of wisdom inside. For the first part, you talked about mathematically equivalent models, right? Looks like a proper way to go. But what kind of mathematical foundation. You use linear-wise, piecewise linear approximation. Are there any other things, tools we can use to do this mathematical proof?
Oh, thank you for the question. This is a very good question. Yes. So far, our starting point is that we use the PLNN as the activation function. But in general, if we have an arbitrary activation function, and as long as the function has some basic structure, for example, differentiable, so that we can use PLNN to approximate such an activation function with a bounded error, then in such a way, we still can guarantee some kind of interpretation quality. I mean, the equivalence will be approximate equivalence.
Mm.
That's in our KDD 2020 paper.
Yep, fantastic. Mm.
Thank you.
Any more questions? Let me ask one question when the audience are thinking, just for the Xiaofang. So actually, I'm also interested in the first part, like, all your targets, I mean, so many ideas, like in terms of interpretabilities, like, like other than LAM, there are so many XAI methods has been proposed. I mean, then my question is, how we evaluate the effectiveness, let alone the efficiency, like just effectiveness of this interpretability method? Because method A said, oh, because of these features, like, the results like that. And method B said, oh, because of that heat map, the results look like that. So what kind of metrics do we have a common knowledge? So we use these metrics to measure all these methods, then this is the best method.
This is an excellent question. And indeed, I did not have that slide with me now, but not long ago, I was giving a talk in a conference. Xiaofang invited me to Jeju Island. And then that discussed the interpretability and explainability. And for many people, they think interpretation and explanation are the same thing. Indeed, they're different things. They're completely different things. Okay, interpretation essentially tells us how the model works in a reproducible way. Okay. So that's exactly what our approach works. We do not say whether the model is correct or not. We just tell you the model make this decision based on these several features and in this process. So this is interpretation. Explanation is much harder. Explanation will tell you whether the decision is reasonable. Meaning, for example, if we have some background knowledge, human expert background knowledge, they can tell you whether the model follows or contradicts with those background knowledge. Mm-hmm. So interpretation is easier to evaluate, because I just check whether the model will always work like that. For example, if I can really detect for the origin model and for your interpretation, whether they consistent with each other. I just hide the attribute whether they still produce the same results. Right. Okay. But explanation is much harder.
So in these cases, so what about causality? Because the people also talk about causality, because like what is the reason cause this result appears? So that is related with interpretability, not explainability, right?
That's more in the explanation instead of interpretation.
Okay, got it.
Causality, essentially you want to say, for example, we see the COVID-19 outbreaks. We try to identify what would be the causes for the outbreaks.
Yes.
A model will just tell you what's the probability. A model may not be right. Right? So interpretation will only tell you, okay, the model says that, but I don't know whether the model is correct or not. Okay. Okay. And causality will tell you, no, indeed, these two things, also the model may not tell you, but by our causality research, I will say they have a good reason to believe there's some relationship.
Okay. Thank you. Thank you. Any
Gary.
Hey, Jen. It's a very interesting talk. I'm not in the computer science field, but I felt I understood a lot of things. So thank you. The question I have is, back to about 40 years ago, right, that AI was very popular, talking about knowledge-based systems, expert systems, those things. So what is kind of the trend? Would that be possible to bring that knowledge to add to this expandability, right? To help understand and explain the model, maybe even sometimes validate the model. So what is the common maybe?
Indeed, the trend doesn't change. Nowadays, we are still building knowledge base. For example, knowledge graphs as a knowledge base. But the difference is that 40 years ago, when we built a knowledge base, we didn't have powerful computation. We didn't have that much data. So we have to use the human beings' brains to do the data processing. So we try to sort of like code the human knowledge into a knowledge base as rules or something. But nowadays, with a lot of data and with a much more powerful computation facilities, we can ask the computers to build such a knowledge base, either by directly storing the data or encode the data, embed data into some high dimensional space in a machine understandable way. But the trend I see is still consistent. There's nothing, big change.
Thank you.
Very good. We have some question from the audience. They type a question in the chat box. Let me read out for you. And the first question from Jianbong Kim, he asking, it seems that graph model is still not being used well because it requires a lot of computing resources. What technology do you think should be developed in order to use it widely, especially in terms of algorithm?
Yeah, wonderful question. Indeed, graph computing, particularly deep learning from graphs, is now a very, very hot topic. Arguably, is one of the hottest topics in machine learning nowadays. You brought up a very important question. Nowadays, quite often you need a quite high bar to use advanced graph computing, graph mining facilities. So that causes inequality for people, for organizations. One idea here, for example, is that whether we can do the knowledge distillation, is that we can build something like the GPT-3, which is a huge model, but still we can distill it into smaller model, more affordable, but still with high quality for individual users, for small organizations. So that is one important thing to do. Another thing is maybe the transferability of models. For example, if we have a big model built, whether this model can be distributed transferred to other problems. And the third thing is how we can let small potatoes to collaborate with each other to build big models. We don't have a huge computational power in one batch, but by everyone contributing some, hopefully we still can get good models. So those are the important directions to go.
Very good. So the second question is about tools to define quality of data sets or validating. Is it is statistical representation?
This is not really well, it really depends on how you say this is statistical representation, because deep learning, in theory, you can reduce it to statistical learning, no problem. More often than not nowadays, people try to use some kind of embedding to represent data so that they can be used or use again for different applications or similar applications.
Yeah, I think the third question is very interesting. Gori is asking, say, like, for the exact interpretations, and if you she understands correctly, such techniques produce a white box model with equivalent express power as the original black box one. So is that possible to find such an exact interpretation for many more machine learning, like deep learning models, like very complex models? If the answer is yes, does it mean that all the black box model can be perfectly replaced because we can always find a one that have equivalent express power?
This is a very good question. First of all, in theory, we can do that. Let me take this back. First of all, if the activation function is a PLNN, then you can do that in theory. But the challenge is the computational cost. For example, if you want to, get the exact interpretation of a BERT model. BERT model is so sophisticated, and you cannot afford the computation because there's so many polytopes. Is the huge number of polytopes. So to that extent, it is not practical yet. And also, from the human point of view, you don't want such a detailed model. Well, when we say the exact, the too exact sometimes becomes overwhelming, right? So how to do the summarization is a very good question to do research. And at this time, people focus more on the exactness, but summarization and is a big area that largely unexplored yet. And don't forget, summarization naturally leads to explanation. Because when we explain things to human being, we don't need to go to every possible details. Instead, we try to generalize that.
Cool, very cool. Any more questions from the audience?
Jen, this is Wei Wan. I'm actually
with UST as well.
Excellent talk, and I just have a few general questions. I wonder if you can comment on the explanation work you have done or the related work with respect to the generalization ability for deep learnings, because I do believe that theoretically we do not have very good models to understand the generalization behavior. And although there are some kind of breakthroughs, but there are actually still quite a lot of competing theory out there. And also in practice, I think it's overfitting quite a lot to the training data. So is it possible that by explaining the current models, as you mentioned, you already can control the complexity to control certain kind of overfitting. So one relation is relating to the generalization aspects of the models. The other thing is that also deep learning models are actually susceptible to certain malicious attacks called adversary attacks. So will this kind of explanation also help in that regard? Thank you very much.
Yeah, thank you. This is indeed a very good, excellent question. Let me first talk about the overfitting issue. The general idea is that the general belief is that if we can have a good complexity measure, we can monitor the change of the complexity when you build a model. And if you see the, for example, the complexity first jump up while the accuracy, for example, does not jump up in the same path, then likely overfitting happens. So you can either stop the current learning process or do some major jumping of your jump start of your parameters so that you can jump out of the local optima. So the challenge is how we can make up a good complexity measure. And we, in our KDD 2020 paper, we make some exercise or exploration on that. There's still a lot of things to do along that line. For example, for sophisticated models, how to measure the complexity. Well, we only can do very simple models, but if you want to do, for example, BERT, and then how you can know the complexity of BERT, okay? That's a very big challenge. Another thing you point out is very, very interesting is adversarial learning. And in that case, we probably may should not use the global complexity measures. And then whether we can look at the local complexity. I don't know exactly what local complexity means here, but the intuition is that if we can look at different the model complexity at different, for example, subspaces of different areas of the problem, either probably not in the original data space, but maybe on some embedding space. If we can look at such things, we may be able to detect some anomaly there. And those anomalies may help us to obtain some hints of possible adversary attacks. That's just some intuition, basic ideas. We have not really done anything substantial yet, but if you have any projects on that, we are more than happy to collaborate on this.
Wow. But I think this would be long, actually. One more question. We have learned about models with explainability, such as decision set, which can be used to explain classifier by showing the rules for making decisions.
Yes.
These years, intensive research effort has been put on explain GNN models. Can you share some common insights, some insight on corresponding interpretable white box model for GNN? How does it differ from those discussed in this talk? Also, what metrics standard do you think can be used to define good explanation or interpretation?
Okay, thank you for the question. This question is very keen and already on the topic. Honestly, we are working on one paper to interpret the GNN. The challenge is the following. Okay, when you do the original CNN, the polytope is easier to form. But for GNN, because the input space is highly different from the vector space, and also you have these graph propagation step. So the polytope is much harder to compute. That's a difference. And if you want to connect these back to the traditional explainability ideas like decision trees, like rules, you can treat each polytope as some kind of rules. And we also have some preliminary results on how to combine polytopes into bigger polytopes. Essentially, you can think about that is something like you combine rules, generalize them into one more general rules.
Okay, so we already overrun. So if no further questions, I have to really, stop here, and then let everyone join me to thank Professor Jian Pei's excellent talk and excellent discussion. I think we really benefit a lot from, the talk and discussion, the question answering, very, very nice. Thank you very much, Jian.
Yeah, thank you so much. Very exciting discussion. Yeah, thank you.
Thank you. Hopefully we can have some time together in the next half year, not this half year.
Looking forward to that. Yeah. Thank you.
In Guangzhou.
Bye.
Thanks, Jian. Yeah.
Thank you. Yeah.